which was that if you write a function f, a complex function f of xy as the real part plus the imaginary part. So in other words, u and v are real functions. Then for this function to be differentiable, for this function to be differential, or which is the same as analytic, the condition was du by dx was equal to dv by dy, and du by dy was equal to minus dv by dx. Right? This was the condition, and this we obtained by just looking at the basic condition for the differentiability, delta x comma y plus delta y minus f of xy divided by delta x plus I delta y, and in the limit delta x, delta y both going to 0, the requirement was that this was well defined, this existed, and it did not depend on which direction, from which direction you are approaching. So here is my point xy, and say here is the point x plus delta x comma y plus delta y. You see, delta x and delta y I can choose in different ways so that these points can be anywhere here. And then I take the limit, so I could come from, I take the limit delta x, delta y go to 0, I can come like that, or I can come like that, or I can come like that, right? So there are infinite number of ways you can approach this point, and the requirement was that this is well defined. It doesn't matter which way you approach. And in fact, we obtained this equation by just studying two ways of approaching. One was the horizontal way, and other was the vertical way approaching. But now what I want to show is that in fact this condition is sufficient. I mean, it guarantees, it doesn't matter whichever direction you approach, if this condition is satisfied, this will have a same value. It will not, the value will not change. Okay? So this is what we want to show. So in other words, this is a necessary and sufficient condition. That's what we're saying. I mean, this necessary is clear because already we saw just by looking at these two directions, we got these conditions. But now we want to show this is sufficient also. Okay. So I mean, one has to make some assumption that first of all, these partial derivatives exist. I mean, we are assuming, of course, that for both the u and v, the partial derivatives exist, right? Otherwise, even these equations don't make sense, right? But I will also assume that these partial derivatives are continuous. Okay, in some neighborhood of x and x of this point, it's continuous. Okay, there's no discontinuity in this partial derivatives. Okay, then you know that okay. First of all, I mean, just think about the partial derivative du of dx, du by dx. Right. This is how is it defined. This is defined as the limit delta x going to 0, u of x plus delta x, comma y minus u of x comma y. So we keep y fixed. And we are changing that x divided by delta x. So this is how it's defined. So of course, when you say this exists, meaning that this is well defined. So what this means is that if I take the difference du by, I mean, so the difference between this. So let's take so u x plus delta x, comma y minus u x y divided by delta x minus du by dx at xy at the same point. This difference can be made arbitrarily small if I take delta x smaller and smaller, right? Because in the limit, this quantity is equal to that, right? So in other words, that the difference between these two, I can make it smaller and smaller, right? By choosing delta x smaller and smaller. So this will be, I can take it to be something less than, for any epsilon which is greater than 0, no matter how small, right? I can always choose delta x such that this is true. Because in the limit delta x goes to 0, this becomes exactly equal to 0, right? So give me any small epsilon, 1 millionth or 1 billionth, 10 to the minus whatever, whatever you choose, give me, I can always find some delta x such that this is true, right? That's the first statement. Okay, so let's then I can write down an equation using this. So let's see, I can write. So this means if I take u of x plus delta x, comma y plus delta y, okay, minus u of xy. I mean, actually, this I can also write it in a slightly different way, which is the same. This is I can just multiply by delta x, both sides. No? So this is the same as saying that u of x plus delta x, comma y, minus u of xy, minus delta x times du by dx, okay, okay, xy, is less than epsilon times delta x. I can write it like this. Okay. So now let's look at this object. This object I can rewrite it as u of x plus delta x, comma y plus delta y, minus, I can just add and subtract one piece, x, y plus delta y, plus u of x, y plus delta y, minus u of xy. So what I have done, I have just added and subtracted this, right? I have done nothing, just added and subtracted the same thing. So now what is this object? I mean, by using this kind of an equation, you see that this is the partial derivative of u with respect to x at y plus delta y, right? So this will be du, this is according to this equation, is delta x times du by dx at x comma y plus delta y, okay, plus some possible correction. I mean, some small change. I mean, right, epsilon delta x. Right. That's I'm just writing these two parts. And this one again, you use this one. Look at this expression. Here I keep x fixed, but I'm changing the y. So this will be the partial derivative with respect to y at xy times delta y, again with another, so let me call it epsilon 1 and epsilon 2, okay, times delta y, okay. So this is what I'm saying. So I can always, because of the fact that delta, I mean, as delta x goes to 0 and delta y goes to 0, this is in fact equal to, I mean, if you divide this by delta x, that's exactly this quantity, du by dx, right? And similarly, if you divide this by delta y, that's exactly this quantity. So for sufficiently small delta x, I can find this epsilon 1 and epsilon 2 such that this equation is true. And in the limit when I take delta x and delta y going to 0, epsilon 1 and epsilon 2 go to 0, right? That's what we said. I mean, in the limit delta x goes to 0, this epsilon becomes 0. Because this by definition is du by dx. So the difference is 0, right? That's what we're saying. Okay, now so far this is fine. But now I want to use the fact that, I mean, this is continuous. We are saying that partial derivatives are also continuous, which means although this is du by dx at x comma y plus delta y, this will be the same as du by dx at x comma y plus some small correction, right? So therefore, where is the here? So this will be equal to delta x du by dx at xy, right? Plus a small correction, right? Which will go to 0 in the limit delta y goes to 0, right? So it will be like delta x is already there, so it will be like delta x times delta y, right? Times something else, I don't know, let's call it epsilon tilde, okay? Okay, that is that. Then I keep the remaining pieces, so the plus du by dy at xy times delta y plus epsilon 1 delta x plus epsilon 2 delta y, okay? Now I can of course absorb it in this here anyway, because you see what we are saying is that when delta x and delta y go to 0, epsilon 1 and epsilon 2 go to 0, right? But this is also the case here. When delta x and delta y go to 0, so I can absorb it here, for example, right? I can just put that together here, this whole thing. Keep delta x a common factor, right? Because after all, what is the property of epsilon 1? Epsilon 1 is something which goes to 0 in the limit with delta x and delta y go to 0. But also, so is this object, right? So you just redefine, just call this whole thing as epsilon 1. Right? I mean, they're all going to 0. That's the important point. The important point is that in the limit delta x and delta y go to 0, this object and that object goes to 0. Okay? So this is what I'll be using, basically. Okay? Or if you wish, you can keep it as it is. It doesn't matter. I mean, you can just put it in. It's more convenient. Instead of writing down these 3 different terms, there's no point writing the 3 different terms because this term is already contained here. I mean, it's already of the same form. So just by redefining epsilon 1, I can just erase that. Huh? So just absorb it inside. Okay. So this is the equation you find. So again, emphasize the important point is that this equation, in the limit delta x and delta y goes to 0, epsilon 1 and epsilon 2 go to 0. So in the limit delta x and delta y go to 0, epsilon 1 and epsilon 2 go to 0. That's the statement. Okay, so now let's write down exactly the same equation for the v. I mean, this was for the u. This was for the u. There will be exactly the same type of equation for the v. So again, let me write down that v of x plus delta x, comma y plus delta y, minus v of xy will be equal to delta x dv by dx at xy plus delta y times dv by dy delta y plus some, let's call it delta 1 delta x plus delta 2 delta y, where again as delta x and delta y go to 0, also delta 1 and delta 2 go to 0. Same expression, same thing. Okay, so now let's do the following. Let's take this equation and add to that I times the second equation, because remember u plus iv is what our function is. So let's just multiply the second equation by I. Just multiply this whole thing. Okay, and add to the first equation. Okay, so now I need to erase this part because otherwise. So I'll just erase this, but you remember these equations. I'll have to use these equations. So these equations you remember, right? Or it's in the notes anyway. Okay, so I do that. So then what I'll get, I mean, this plus that is simply what I call f, right? So it's just simply f of x plus delta x, comma y plus delta y. And this one is simply f minus f of x y, right? That's equal to, so here delta x, so let's look at, so you have a delta x, so I have to write it. Let me do the following. We know du by dx is the same as, I mean in this equation, sorry, look at this part here. This was the last expression, right? dv by dy is the same as du by dx, right? That was the one of the Cauchy-Riemann conditions. So let me just write it. Can I replace it here already? Huh? So by using Cauchy-Riemann conditions, this becomes du by dx, right? Similarly, you can replace, say, for example, this one. Du by dy is minus dv by dx, right? So I'm just writing everything in terms of partial derivative d by dx. So du by dy is minus, there is a minus sign, okay? So I can write it as minus dv by dx, okay? So here's where I've used the Cauchy-Riemann conditions. Because what we want to show is that Cauchy-Riemann conditions are sufficient, right, for a function to be analytic. So I'm assuming Cauchy-Riemann condition is satisfied. Then I want to show that this function is differentiable. Okay. So this is equal to, so let's look at that. So du by dx appears in 2 places, right? What is that? I have written delta y 2 times. Sorry, there's only one delta y. Okay. So I take delta x plus, you remember I multiply I to this equation. So this becomes delta x plus I delta y, right? So you get here, so let me use a symbol, delta z is equal to delta x plus I delta y. Okay. So then what we are saying is delta z times du by dx at xy. Okay. And now look at the second term, dv by dx. This is what is appearing here is, so dv, so let me write down. So dv by dx is multiplying minus delta x, delta y from this term. Then I'm adding to that this term, but I have to multiply by I. So you get here I plus I times delta x, right? But this is the same if I take out an I factor. So this is the same as I dv by dx, and then you see it's just delta x plus I delta y again, because I square is minus. So again it's delta z, right? So again I can write it like this, delta z plus I dv by dx at xy. Okay. So that I have taken care of these two, all these pieces, the partial derivative pieces. Now I have to worry about these pieces here. So here I just get, so this one is simply epsilon 1 plus I delta 1 delta x plus epsilon 2 plus I delta 2 times delta y. So this is the equation we are finding. And once again, I remind you that in the limit when these two delta x and delta y go to 0, these coefficients also go to 0, right? Because all these epsilon 1, epsilon 2, delta 1, delta 2 are vanishing. Okay. So this is the important point. And now let's divide by delta z, both sides. Because after all, I want to divide this by delta z, this combination. Remember that was the definition of differentiability. And then I want to take delta x and delta y go to 0 limit. So divide. So you get here f of x plus delta x, y plus delta y, minus f of xy divided by delta z. Okay. And let me also put this on the other side. So minus du by dx at xy plus I dv by dx at xy. Okay. So can I erase this line now? Huh? This line I erase? Okay. This is equal to, remember I'm dividing by delta z, right? So this is delta x divided by delta z times epsilon 1 plus I delta 1 plus delta y divided by delta z epsilon 2 plus I delta 2, right? That's the equation. So this is at the level of it's a complex equation, but since this is we are saying this is equal to that, also its magnitude will be equal, right? So also this magnitude will be equal. I use this symbol when I put this vertical lines. It means I'm taking the magnitude of this. You all know what is the magnitude, right? I mean, if I give you some complex number a plus ib, there's a complex number where a and b are real. Its magnitude is simply square root of a square plus b square. Okay. So I mean, this is like if you plot, so a is the real part and b is the imaginary part. Okay. So this will be some point here, right? With a being the real part. So if I draw a perpendicular, this is a and this is b, right? So what this magnitude is, it is just the length of this vector. The length of this vector is square root of a square plus b square using Pythagoras theorem, right? So that's what I mean by the length. So since if a complex number is, if the two complex numbers are equal, obviously their lengths are also equal. So what we have is this. Okay. Now, you know that given this length satisfies a triangular inequality, right? We have seen that in the first chapter. With the triangular inequality. Right? So I have two complex numbers. You see, complex number is, you can think of complex number as the same as a vector in two-dimensional space, because a complex number defines to you a point in the complex plane. So you have a vector there, right? And indeed, when you compute the length is just the length of the vector. So say this complex number, so again so this complex number is some vector, let's say, and then that complex number is another vector, okay. Then what we are saying is that take the two vectors, add them up. When you add them up, it is this, you arrive at that, right? So this is the addition, and the statement is the length of this is less than or equal to the sum of the two lengths, right? That's what it's saying. So the right hand side is going to be less than or equal to the length of individual vectors. So which means delta x over delta z times the length of epsilon 1 plus I delta 1 plus the length of delta y over delta z and length of epsilon 2 plus I delta 2. Okay. Now, if you look at, I mean, so it was the length of this whole thing plus the length of this whole thing, but you know, magnitude of a product of two complex numbers, length of product of two complex number is equal to the length of one complex number times the length of another complex number. Is that is right? Yeah. Is that clear? No? Maybe I should write it. Okay. So what I'm saying is that if I'm given two complex numbers, say a plus ib and times c plus id, its length is the same as the length of a plus ib times the length of c plus id. Okay. That is so because after all this length, length is what? Length is you take the complex number, multiply by the complex conjugate of that number and take the square root, right? After all, that's what this is. I mean, if you look at this object, this I can also write it as square root of a plus ib times a minus ib, right? Because just open this up, you get a square, and then if you look at this, this becomes b square because I times minus I is plus 1, b square, and the cross terms vanish. You have a plus iab from here, but then there is a minus iab, it cancels. So this is the same as that, right? So magnitude of this complex number is simply this times its complex conjugate and square root, which is the same as a plus ib, a minus ib, c plus id, c minus id, square root, right? But if you look at here, this length is this times its complex conjugate square root, which is that part, right? And this length is this times complex conjugate square root. So this is indeed true, right? So length of the magnitude is called usually magnitude, which is the same as length when you think in terms of a vector. Magnitude of a product of complex numbers is the product of the individual magnitudes. Okay, so that's what I used. That's what I used here. Triangular inequality says the magnitude of that plus the magnitude is less than or equal to magnitude of that plus the magnitude of that, right? But then I use the fact that magnitude of this is the same as product of the two magnitudes. That's why I written like that. Similarly, the other one. Okay. Now, delta x by delta z, you see delta z is this. So what is the magnitude of this? Well, this is the same as length of delta x. I mean, this delta x is a real object. So when I say magnitude, it means absolute value, right? Because it could be plus or minus in general, no? Positive or negative it could be. I just take the absolute value. And then what is the length of delta z? It's a square root of delta x square plus delta y square. This is surely going to be less than or equal to 1, right? Similarly, delta y over delta z, length of magnitude of that will also be less than or equal to 1, right? So we are saying, so therefore what we have is that this whole thing is going to be now. I mean, I want you to remember this. I will erase this part, but I want you to remember this, that what we had in the original equation was that in the limit delta x and delta y go to 0, each of these epsilon 1, delta 1, epsilon 2, delta 2, etc. go to 0, right? This is what, so this is the statement here. I will just erase that part. So at the end of the day, what we are saying is this is less than or equal to the length of epsilon 1 plus I delta 1 plus plus the magnitude of epsilon 2 plus I delta 2. right? Because after all, this number is less than or equal to 1, right? So actually, this is going to be even less than, I mean, this is going to be even less than that, right? Okay. Now you take the limit delta x and delta y go to 0, right? Then right-hand side vanishes, right? That's what the statement was, that in the limit delta x and delta y go to 0, these two go epsilon 1, epsilon 2, delta 1, delta 2 go to 0. So this right-hand side becomes 0, which means this left-hand side must be also 0, right, in the limit. So you see that we have shown here that this is well defined, because if this has to be 0, this quantity is equal to that complex number, and it doesn't matter which way you are taking the limit delta x and delta y go to 0. See? So that is the proof. Yeah, I mean, yeah. Okay. I mean, it may look a little bit more complicated than what it is because of all these epsilon delta prescriptions and so on. No? But yeah. Okay. So I just wanted to convince you that Cauchy-Riemann condition is a necessary and sufficient condition for the function to be differentiable. That's the main thing. Now, if you don't have any question on that, let me go back to remember towards the end of last lecture, I tried to explain to you what is the meaning of this Cauchy-Riemann condition. And I said that it basically means that the function is function only of z, not z bar. Right? So now let me try to, that was a bit intuitive. It was not very rigorous. That statement was not very rigorous because I use this partial derivative d by dz and d by dz bar, right? And use the chain rule. But to say partial derivative d by dz bar, it means like you are saying I will I'll keep the z fixed and change z bar, right? I mean, what is the meaning of partial derivative with respect to x? It means I keep y fixed and I only change x, right? But when you say partial d by dz bar, partial z bar, that doesn't make much sense because, I mean, that means I have to fix z but change z bar. But that cannot be because z is complex conjugate of z bar. So that's why I put a quote unquote in that. So now what I will do is I will, without going through that kind of an argument, I will still try to prove to you that function is only a function of z if it is differentiable in this sense. If it's, as I said, if a function is differentiable, then you call that function as analytic function, right? Yeah, actually for analytic function it's a little bit more than that. I mean, analytic function means that it is not only differentiable at that, when you say a function is analytic at a particular point, you mean that it's not only differentiable at that point, but also in some small neighborhood of that point, right? Right? So it's a little bit even going beyond that, just one point. Okay, so I can erase this. So what now I will try to show is that if a function admits a Taylor expansion around some point, and suppose it's differentiable at that point, then that implies that that function. So okay, let me write down. So what is a Taylor expansion? If it's a function of one variable, you can Taylor expand around some point x naught, right? And the way you do it is this is f of x naught plus x minus x naught df by dx at x naught. Everything is evaluated at x naught, plus 1/2 x minus x naught square d2 f by dx2 at x naught, and so on. Right? A general term would be 1 over factorial n x minus x naught to the power of n dn f by dx n at x naught. This is a Taylor series. You probably remember from the. Well, this is for one variable, but now for us we have f depends on two variables, x and y. Okay, so you have to do a double Taylor expansion, because what will happen? You can do step by step if you wish. So now it's a function of also y. So this is a function of. So this is evaluated at x naught. So as far as x is concerned, it becomes x naught, but you have a y here. So everything you see depends on y. And what you can do is now take each of these objects and expand, do a Taylor expansion with respect to y. So it will become double sum, right? So f of xy then, okay, so first of all I have to replace this ordinary derivative by partial derivatives, right? So because now you have two variables, so this will become partial derivatives. Okay, and then I do a second expansion of each of these guys with respect to y. So that results in a double expansion, and this can be written as sum. I'll just write directly sum nm 1 over factorial n 1 over factorial m x minus x0 to the power of n y minus y0 to the power of m, and dn by dxn dm by dym f xy evaluated at x0 y0. So this is the double Taylor expansion, where n and m go from 0 to infinity. And the 0 means no derivative. That's the first term, f x0 y0. And, okay. So this is the expansion. Okay. So actually, I can rewrite it in a slightly different way. I mean, I have a double sum, n and m going from 0 to infinity. So you can write it in this way, and I will just explain. First, I mean, when I change n and m, this the order of the derivatives increases, right? The total number of derivatives you're taking is n plus m, right? Okay, now out of the n plus m, n of them are x derivative and m of them are y derivative. So let's do the sum in such a way. I keep first the total number of derivatives I take, I keep it fixed, right? And then you see what I'm saying. Keep n plus m fixed first. First I keep n plus m fixed. Okay? And then, so let's say n plus m equal to say 4, for example. Suppose I keep that fixed. And then you see now I have to distribute all possible ways. I can distribute say 4 x derivatives and 0 y derivatives, right? Or I can take 3 x derivatives and 1 y derivative, right? So this is the numbers of d by dx, and this is the number of d by dy, the second one. Huh? Or I can take 2 2 or 1 3 and 0 4, right? So I have all these possibilities I have to take into account. And then after doing that, then I sum over all possible n plus m's. So you see what I'm saying? So this I can write in so k going from 0 to infinity. So k is the total number of derivatives. Okay? And then I have to distribute this k in say n and k minus n, right? So if out of this k there are n x derivatives, then there should be k minus n y derivatives, right? So I have to sum over all possible n. This n is not the same. Let me put a different symbol, L. L going from 0 up to k. Maximum is k, right? And then you have d by dx to dl by dxl and d k minus l dy k minus l. Okay. So this L goes from 0 to k. And then I have x minus x0 to the power of L and y minus y0 to the power of k minus L. Because this power is the same as that number of x derivatives, and that's the same as number of y derivatives. And then I have 1 over factorial n. N was this number of x derivatives, so it's 1 over factorial n, and then 1 over factorial k minus L. It's just a way of rewriting this. This double sum I can write in this way. Now the nice thing about this is that this sum is a finite sum. Right? The only infinite range sum is that. Okay, f of xy. Okay. I mean, this is if you this is very useful. I mean, many of the computation, this type of things becomes useful to change the way you sum. No, so what I mean, if you think about this n and m, so in the original thing n and m, so we are summing over all the integers, right, from 0 to infinity, n equal to 0, 1, 2, etc. Similarly, m equal to 0, 1, You have also n equal to m equal to 1. So you're summing over lattice points, a set of lattice, infinite lattice, right? You're summing over all of these points. I mean, this point means n equal to m equal to 1. Okay? This point means n equal to 2 and m equal to 1, etc. So because this is a free sum, n and m going from 0 to infinity. So you're summing over all of this infinite number of points here, right? Now this way of writing it is what we're saying is that you keep n plus m fixed. Okay? So look at this here. So I have like this. This is n plus m equal to 2. This is this n plus m equal to 0. That's n plus m equal to 1. So you see, if you look at that, here k is 0. On this line k equal to 1. On this line k equal to 2. Okay? This one k equal to 3, etc. Right? I mean, you see, this is n. This is n equal to 2, m equal to 0. So it's 2 comma 0. This is 1 comma 1. This is 0 comma 2. So in each case, when you add n and m, which is what I call k, this is 2, right? For here, everything this is 3 0, 2 1, 1 2 3, 0 3, right? So this is k equal to 3, etc. So what we are doing is we have to sum over all the values of k, and for each value of k, I have to sum over these numbers. Yeah. So this is indeed, you can see that for k equal to 3, n can be 0, 1, 2, and 3, right? That is the second. L is from 0 to k. This is the way. So it's just a way of writing, which is convenient way of writing. Okay, fine. So far, this is what it is. Now I have to use a Cauchy-Riemann condition. I mean, this is for any function which which admits a Taylor expansion. Okay. So when we say admits a Taylor expansion, means of course in this there are all the arbitrary derivatives are appearing. So we are saying that this function has all possible partial derivatives, right? And second statement we are making is that there's a non-zero radius of convergence. After all, this is an infinite series, right? It may not be convergent, right? But there is some radius of convergence around x0, y0, where this series converges. Okay? So you can trust in that region. Okay. But now I have to use a Cauchy-Riemann condition. So let's see how we can use. So we have to use a Cauchy-Riemann. Right? So let's look at this object. So you have dl. So let me first look at, So you have, this is simply u of xy plus I, this is the f of xy, right? Plus I v of xy. Okay. So let's see. So let me take d by dx of f. The partial derivative with respect to. Well, this is the same as du by dx at xy plus I dv by dx at xy. Yes? Correct. Okay. And similarly, df by dy xy is du by dy xy plus I d v by dy xy. Okay. Now I use the Cauchy-Riemann condition, and I will convert everything into all the d by dy into d by dx by using Cauchy-Riemann conditions. Okay. So this will become, by using Cauchy-Riemann condition, this is the same as minus dv by dy dx at xy, right? And using that's I du by dx at xy. Right? But this is the same if I take as I, if I take out common factor I, this is the same as du by dx at xy, okay, at xy, plus I dv by dx at xy. Right? Because I square is minus. That's it. But that's the same as that, you see. So what we are seeing is that this is the same as I times df by dx at xy. This is where the Cauchy-Riemann condition is appearing. Okay. So now I can just, wherever I find y, d by dy, I can just replace by I times d by dx. Right? So in particular, so this I rewrite. as sum k equal to 0 to L infinity, L 0 to k, 1 over factorial L, 1 over factorial k minus L, and then you have x minus x0 to the power of L, and y minus y0 to the power of k minus L. And then I replace each d by dy by I times d by dx, right? I mean, this in particular implies this implies also that if I take n number of derivatives, dn by dy n of f, this will be the same as I to the power of n d by dx n f, right? Because you just keep repeatedly applying d by dy. So you will get this. So this becomes then I to the power of k minus L, okay? And then d by dx to the k minus L, but this is also d by dx to the L. Put them together, it's simply d by dx k times acting on a x, y. Okay. So now you see this has L has disappeared here. This is at x naught, y naught. There is no L here. The L dependence is only in this part. You see this part here. I can sum over L. It's a finite sum, I can sum it over. But this is nothing else but a binomial expansion, right? Can I erase this now, this part? You remember the binomial expansion. If I have some, let's say, a plus b to the power of, let's say, k. Suppose I want to look at this expansion. This is nothing else but, say, the combinatoric factor kcl, right? A to the power of L, b to the power of k minus L. Summed L going from 0 to k, where what is kcl? The combinatoric factor is factorial k divided by factorial L times factorial k minus L. Yeah, this is a binomial expansion. Is this just, I mean, in this you have k products, so you see which term, I mean, you look at the term which has L A's and k minus L B's, right? And then you see how many ways you can get it. So you want to pick L A's out of, I mean, so what is this? This is A plus B, k times, right? So there are k times this is appearing, right? So you see, if such a term will appear when you take out of this k possibilities, I take L A's from there. Then of course the remaining must be B, so that's why it's k minus L. So it's a question of the combinatorics, right? Out of the k things, you want to pick up L A's. And how many ways you can do that is just that number. That's the combinatoric. So this is what's called the binomial expansion. Okay. So you see, if you look at that now, take A to be x minus x0 and B to be I times, I mean, B is what? Everything which appears with the power k minus L. Now look at what appears with the power k minus L. It is this and that. So it's I times y minus y0 to the k minus L, right? And then this combinatoric factor is exactly right, except for this 1 over factorial k is missing, right? So let me multiply and divide by 1 over factorial k. So let me write it like this. This is equal to sum k equal to 0 to infinity 1 over factorial k, and put also factorial k here. I did nothing. I just multiply and divide by the same quantity. You see, this does not depend on L, so I can do that. I can take it out here, right? Then this is simply KCL, the combinatoric factor. So that entire thing simply becomes x by A, which is x minus x0, plus I times y minus y0 whole to the power of k. Okay? So we get the expression finally that this is equal to sum over k going from 0 to infinity, 1 over factorial k, and then you get here x minus x naught plus I times y minus y naught whole thing to the power of k d by dx k, dk by dx k f at evaluated at x naught y naught. I mean, these are some numbers, because this is evaluated at some particular point. Those will be some numbers, right? The only x and y dependence is all here, right? And notice it's coming with x plus iy, which is what we call z. So this is nothing else but this is z minus z0, z0. Z0 is the point around which you are expanding. So z minus z0 to the k. See, there is no z bar. That's what I'm saying. So this function in the Taylor expansion appears only z appears, not z bar. This is an important point. Yeah? So that is the yeah. So here you see in this argument I didn't use this kind of undefined, I mean not well defined d by dz bar partial derivatives, right? Here I didn't use that. I just used the Cauchy-Riemann conditions, and you see that it's only a function of z. Okay. So now. Is it clear? I mean, any question on that? Yeah.
When you are changing the d dy f of x y to be I
D by dx.
d by dx, you are adding the powers.
Yes, yeah. Because I mean, so this is replaced by d by dx to the power of k minus l, right? This means you are taking k minus l derivatives with respect to x. And now this is you're taking further l more derivatives, right? So the total number of x derivatives is k, right? So that's what I put there. Yeah. I mean, actually, we will see later on that for analytic function, there is always a Taylor expansion. Like you see, this is exactly a Taylor expansion. It's 1 over factorial k, z minus z0 to the k, and then there's some numbers. These are some numbers. So there's a Taylor expansion. So for every analytic function, there's a Taylor expansion in some neighborhood of a given point, which of course, in particular, means there are arbitrary number of derivatives. So I mean, so that's so we'll see that. Yeah, the derivative of f of an analytic function is itself again analytic. We'll see that. So therefore, that's also differentiable, and then this goes on. So differentiable in this sense, in the complex sense. Okay. So now, yeah. So maybe I should give some perhaps examples of analytic function. Right. So, yeah. Okay. Let's see. So I can erase everything now. Yeah. This is given. This thing is given here in page 16, the equation 4.12. That is where. Yeah, that's where it's given there. Yeah. Yeah, I should make one comment about this. Again, Cauchy-Riemann conditions. Du by dx equal to dv by dy, and du by dy is minus dv by dx. Right? If you take these two equations, let's do the following. Let's take the d by dx of the first equation, x derivative of the first equation. So if you take the d by dx of this equation, you get here d2u by dx2. That's equal to d2, d by dx, d by dy of v, right? That's the first equation. And for the second equation, let's take d by dy, the second equation. Then you find here d2u by dy2 is equal to minus d by dy d by dx of v. Now add the two equations. You see the right hand side becomes 0 because partial derivatives commute. The ordering doesn't matter, right? So when you add them up, this right hand side vanishes and you get d2 by dx2 plus d2 by dy2 acting on u is 0. Okay? Which means the u satisfies the Laplace equation in 2 dimensions, xy plane. Similarly, you can also do the other way. You take now d by dy of this equation and d by dx of this equation and subtract. Right? So then this will cancel and you will get d2 by dy2 of v plus d2 by dx2 of v is equal to 0. So you get here d2 by dx2 plus d2 by dy2 v is equal to 0. So what we are saying, by the way, the functions which satisfy Laplace equation are called harmonic functions. Okay? That's a definition. So any function which satisfies that Laplacian acting on that function is 0 is called a harmonic function. Okay? So what we are saying is that u and v both are harmonic. U, v are harmonic. Harmonic functions in 2 dimension, of course. I mean, the harmonic function is in general, even for any dimension. If something satisfies the Laplacian acting on that function is 0, you call it a harmonic function. But in particular in 2 dimension, because after all we are talking about 2 dimension, complex plane is 2 dimensional. So u and v are harmonic. So it's see, they are very restrictive, right? I mean, you see, analytic functions are very restrictive. We are saying that the real part and imaginary part of the analytic function must be harmonic function, must satisfy Laplace equation. Right? But it's more than that. I mean, it's not just that you pick up any arbitrary harmonic function here and any arbitrary harmonic function here, but there is a relation between these two via Cauchy-Riemann condition. Okay. So that was one thing. Okay, I mean, there are some more discussions here in page 17 to say a little bit more about this. Okay, I will skip that. It's not because it's not so important. I mean, I will skip that. Okay. Now, let's see. I mean, now we have defined the notion of differentiation, right? I mean, this complex sense, what we mean by d. I mean, we call that as df by dz, that limit. If that limit exists, then we call that as df by dz. That was a definition of df by dz. So we have defined we have given a definition of differentiation with respect to z. Now we would also like to talk about integration, right? Okay. So how you integrate? So the integral, I mean, we would like to define as some integration. I mean, so you would like to have something like f dz integral. Just like you have df by dz we have defined, now we would like to give a definition of this quantity, f times f dz integral. But after all, dz is nothing else but dx plus I dy, because z is x plus iy, right? So it's a one-dimensional integral, because there's only either dx or dy. It's not a dx dy. If there was a dx dy, it would have been a 2-dimensional integral, right? But each of these terms, I mean, this will become a sum of 2 terms, right? This is f dx plus I f dy, right? Each of them is a one-dimensional integral. So this integral will be defined on a curve in the complex plane, right? So you have this complex plane xy, so since this is a one-dimensional integral, you can define it on a contour, on some curve, one-dimensional curve. Okay. So take this of some one-dimensional curve, arbitrary curve, choose any curve you wish, and there you can define this integral. In the following way, I will define what I mean by that. So what you do, you just, as usual, you just the way you define the integral is you just split it into tiny pieces, small pieces, okay, and then you just pick some point inside randomly, pick some point, evaluate the function at that point, and then multiply by dx. Between these 2 points there will be some delta x and delta y, right? So you see what I'm saying. So maybe I should expand this a little bit, make it a bit bigger so that you can see. So how is it defined? So let's see. I have some contour, and then I divide into these are supposed to be very small, but I'm drawing it big so that you can see. Okay. So at this point we'll have, let's say, some point x y. Okay. This point will be some x plus delta x, comma y plus delta y in general, right? So what you do, you take some point here in somewhere, some in between. Let's call it x prime y prime. Okay. Evaluate this function at x prime y prime, and multiply by this difference. So but it's dz combination, so it will be delta x plus I delta y. So multiply this by delta x plus I delta y. Okay. And then sum. You do that for each of these pieces and sum them up, right? That is the definition of the integral. Of course, in the limit where this spacing, these points start coming closer and closer to each other, right? Because if you just do that, this will be this will have a lot of error. I mean, if you have big intervals, right, it will not be exactly the same as integral. It will be there will be big error, right? But as you start taking this interval smaller and smaller and smaller, right, that will be the definition of the full integral. Okay? Of course, one is assuming that the limit exists, the limit of this procedure. So let's say I divide this into n pieces, into some capital N pieces, n number of pieces. N is large. Of course, when n becomes large, these separations become smaller and smaller, right? So you evaluate. Let's suppose the distance between each of these separations is epsilon, let's say. So n times epsilon is like the length of this thing, right? So this is fixed. The length is fixed, of course, given a curve. But so you take n to infinity limit, which is the same as taking epsilon to 0 limit, right? So in that limit, the spacings become smaller and smaller. And if the limit exists of this sum, when you take this sum, if the limit exists, then you say that function can be integrated along that curve. This is the standard definition. This definition of integral is the Riemann definition of integral. Riemann introduced first this definition of integral. Right? You have to define what you mean by the symbol integral. So this is defined precisely like that. You divide into large number of pieces with the small intervals, and then you take the limit. The number of pieces become infinite with the spacing going to 0. If the limit exists, then you say that function is integrable. So the same definition, same Riemann definition, we just apply for the path, for a contour. This is called a contour, because it's a one-dimensional curve inside two-dimensional space. This is called a contour. So you say it's a contour integral. This contour integral satisfies all these usual statements. So if you take say, suppose f itself, was itself some derivative of some other function. In this derivative being defined, we already defined in what way, what is the sense of this differentiation. So say there's some capital F, which is an analytic function, so therefore df by dz is defined, right? And then we are saying, suppose the little f is some another function which is just which is this function, right? Df by dz. Then the integral on any contour of this function f, which are in other words df by dz is the same as f evaluated at the end points. I don't know, let's suppose the initial point is some z0 and final point is some z1, right? Then it will be simply f evaluated at z1, or let me write it here. Suppose the initial point was x0, y0, and the final point is say x1, y1. Okay, in this contour. So here this point is some x0, y0, and the final point is x1, y1. Then this is nothing else but f of x1, y1 minus f x0, y0. This is the usual thing that this you are familiar with, right? I mean, the integral of a total derivative is just the value of the, that object at the two endpoints. We have to take the difference, of course. This depends on this sign depends on what is the arrow. I mean, you are integrating from here to there or from there to here, right? If you are integrating from here to there, then it will be x1, y1, and here is x0, y0. Then it will be that answer. But if you are integrating from here to here, then it will be other way around, right? That's the usual. I mean, the upper limit minus the lower limit. So that is the. So you have a sense of direction, arrow, whether you're integrating from here to there or from here to here. If you integrate from here to there and compare it with the answer that you would get when you integrate from here to here, they are just minus of each other, right? That's just the minus. Which is also clear from the definition of the Riemann integral, right? When you divide into small pieces, when you're doing it this way, you take the delta z here. So this minus that. But if you're doing it this way, you're doing this minus that. So it's a minus of the previous result. I mean, that's an important point to remember. I mean, we'll use it many times. I mean, this kind of thing. So if you have an integral over a contour this way, you get something, right? But if you do the other way, you will get minus of the previous result. Okay. What else now? There is one inequality which you can prove, and that's a very useful inequality which we'll again and again use. So the inequality is called Darboux inequality. Darboux inequality. Okay. So the statement is this: suppose I take some analytic function. These are analytic functions. I'm taking an analytic function f of z dz. And take. So let's call this in some contour. Some contour is given. That let's say that contour, and then so okay, the integral will be some complex number. Okay. So I want to get some bounds on this complex number. I mean, you know, usually the bounds, like you remember the proof I gave in the beginning for the Cauchy-Riemann conditions being sufficient. I was using all this quantity is going to be less than or equal to something like bounds. You use a lot of bounds in various proofs. So in many of the proofs, you need to find a bound for this function, okay, upper bound for this function. So in particular, if you take the modulus of this, okay, modulus of this will be some positive number, right? Always modulus of any complex number will be positive number. So you want to get a bound for that. This quantity is going to be less than or equal to something. Okay. So the bound. So the way to obtain the bound is that let's first of all use the Riemann definition. So what we did. So let's say we divide this into n pieces. Yeah. So let's say this I call z. Let's draw it differently. So here is my contour. So here is I start my z0, then you have z1, z2, all the way up to zn. So I've divided into n pieces. My starting point is z0 and the final point is zn, and I just divided into n pieces. And I call this z1, z2, etc., etc. So and then choose some points here in the intermediate, anywhere inside, and call those points psi1 is a complex number, just a coordinate there, psi2, etc., psi3, etc. Then by Riemann definition, this integral, so the integral is simply sum f evaluated at zn minus f evaluated at zn minus 1. F at psi n and times z n minus Zn minus 1, right? So I take, so look at the nth guy. So this is say Zn minus 1, and that is Zn. And here is some point psi n. So I evaluate the function f at psi n and take then multiply by this difference, Zn minus 1. Okay? And then sum over n going from 1 up to capital N. Right? So when n equal to 1, you have a Z1 minus Z0, Z0 times f evaluated at psi 1 and so on, all the way up to the last point. This will be Zn minus 1, and here this is what I call psi n, some point inside. Right? This is the reminder. And then, of course, I have to take the limit. I have to take the limit capital N going to infinity. Right? But so let me just define this as capital N. So this is this number, and finally the I itself is defined as capital N going to infinity of this I capital N. Right? I mean, I is the limit if it exists. I mean, assuming of course it exists, n going to infinity of I n. That is that. Right? This is the definition of Riemann. This I'm just using Riemann definition of integral. Okay. So let's first get a bound. We want to get a bound for I, right? But first let's try to get a bound for I n. Okay. So let's take this modulus of I n. And now this is, of course, there is a sum of several complex numbers. Then you again use a triangular inequality, that the modulus of a complex, if a modulus of a sum of complex numbers is less than or equal to sum of the modulus of individual complex numbers. So use triangular inequality, so you get less than or equal to sum n equal to 1 to capital N f psi n modulus, and then modulus z minus zn, zn minus zn minus 1. Okay. So, okay, this is what it is. But now if you look at, I mean, the modulus of f at this any of these points here is obviously, I mean, if you look at the modulus of this f at any point here, since f is going to be is finite, right? Because if it was infinite, you cannot even integrate it. It will, right? So of course I'm saying f is bounded. I mean, f is finite, right? So therefore, modulus of f will have some maximum somewhere as you move along the curve, right? So whatever this is, it is going to be less than or equal to maximum of f, maximum of the modulus of f in that contour, on that contour. I mean, just look at all the points here. At each point, the f will have some modulus, right? Look, it will have some maximum. So this is what I mean: f maximum of f on that contour. So what? So obviously this is going to be less than or equal to that, because this by definition is the maximum, which is a finite number, because f is bounded. So that's that. So and this is of course independent of small n. This is some number. I can take it out of this sum, right? So this will be n equal to 1 to capital N modulus of Zn minus 1. Okay. Now look at this here. So I mean, okay, here. So Zn minus Zn, this curve. I mean, let me try to make it more curved, because here it looks almost straight. Let me. I'm just trying to make it. So suppose I have Zn here, Zn minus 1 here, and Zn there. Okay. So what is this object? Zn minus 1 is simply the length of this vector from here to here. But this length of the vector is going to be less than or equal to the length of this arc, right? I mean, it will be equal if this arc itself happened to be the straight line, right? Which could have happened. But if it is not a straight line, it will be certainly greater than the straight line length, right? So, so this is going to be less than or equal to the arc length. Let me just call it Ln. Ln is the nth arc length. And then when I sum from n equal to 1 to n, it is just the total length of the arc, total length of this curve, right? So this is going to be less than or equal to max f on that contour times the length of the contour. I don't know, let's call it L, length of the contour. This is the length of the contour. So this is the bound. I mean, the proof is completely trivial, right? I mean, it's very straightforward proof. And I mean, it looks, I mean, looking at this statement, it doesn't look like it's going to give you some very useful results, no? However, it turns out in many theorems, this is very useful. Okay, this we got a bound for I capital N, right? But notice that this thing does not depend on capital N. This only depends on the property of the contour and the function, how the function behaves on that contour, right? So this is true for any capital N, and therefore, in particular, in the n going to infinity limit also, right? So this is the conclusion, that final conclusion is this is less than or equal to max of f, modulus of f, on that contour times the length of the contour. This is that inequality. It's a very useful equality. Okay. So now, okay. So two things I could do. One is, of course, one of the very, very important theorem, and that is the Cauchy theorem. Should I do that first? Okay, there is a section which I will skip, and that section is section number 9, conformal transformations. I will skip that. Yeah, conformal transformations. Okay. I will skip that because I think you will not need it too much. So, and you know, you want to learn about conformal transformations. Okay, let me do the following. Let me proceed with the thing, because there are more important things. Then if I get some time, I'll come back and do the conformal transformations. To follow the rest of the chapter, you don't need to know the conformal transformations. So it can be done independently. Okay. Perhaps maybe I should just give some examples of this, of analytic functions. Let me just take some examples before I discuss the, there's a very important theorem, Cauchy theorem. Which is, okay, so some examples of analytic function. Okay, the simplest example is z itself. Take the function to be z. This is analytic. You can show that, well, this is x plus iy. So real part u is x, so that means u is x and v is y, right? And it clearly satisfies the Cauchy-Riemann condition. I mean, Cauchy-Riemann condition is du by dx equal to dv by dy, and du by dy is minus dv by dx, right? I mean, this is 1 for this choice of u and v. This is 1, that is 1, and this is 0 and that is 0. So it's trivially satisfied. Let me see. By the way, you can also prove one thing, that if I give you two analytic functions, f1 and f2, suppose these are analytic functions, right? So f1 is u1 plus iv1, and f2 is u2 plus iv2. And they satisfy Cauchy-Riemann conditions. So let's say ui, I going from 1 and 2, right? And this is satisfied. That's why I'm calling them analytic function. Then you can show the product f1, f2 is also analytic. Okay. So what is f1, f2? Let's multiply that. So you get here you multiply and collect the real part. So the real part will come from u1, u2 minus v1, v2. Okay. Plus the imaginary part, which will be u1, v2 plus v1, v2. Okay. So this is, let's call this some capital U and this capital V. So we want to check whether capital U and capital V satisfy the Cauchy-Riemann conditions. If they do, then this is an analytic function also. So that should be, let's see if it's true or not. So we want to check, let's say, the first equation. So d capital U by dx is equal to d capital V by dy. So substitute that. I mean, this is a question mark. So let me start from here. This is equal to d of u1 u2 minus v1 v2 by dx. And we want to, so which is, let's open this up. So here there will be many terms. Du2 by dx plus du1 by dx u2 minus dv1 by dx v2 minus v1 dv2 by dx. So that is this one. And look at the dv by dy. What is capital V is that, so which is the same as d of u1 v2 plus v2 plus v1 u2 by dy, which is u1 dv2 by dy plus du1 by dy v2 plus dv1 by dy u2 plus v1 du2 by dy. So we want to say that these two are equal, right? So let's use the Cauchy-Riemann thing. So for example, let's say look at this term which comes with the u1 and u1. du2 by dx is the same as dv2 by dy, right? So these two are equal. So this cancels from that. Look at the u2 term. u2 is this. So du1 by dx is again dv1 by dy. Okay. So this is there, goes out. If you look at the v2, du1 by dy, but that is equal to minus dv1 by dx. So this also goes out. And finally, the same way, v1, again use the Cauchy-Riemann condition. So this also. Okay. Similarly, you can check the second relation also. I mean, I will not go through that. It's simply just open it up and use that. Okay. So that's an important result. I mean, if you two analytic functions, product is again an analytic function. So as a result now, since I know z is an analytic function, z square is also an analytic function, z cube is also an analytic function. In fact, any power of z is an analytic function, right? In other words, of course, the sum of two analytic functions is also an analytic function, right? That is clear because, yeah.
It doesn't satisfy the other condition.
The second condition is satisfied, right? Because
Del y equals minus del v del.
both are 0, right? We take
Okay, 0.
both are 0 equal to 0. So then, yeah. Okay. So as a result, then any polynomial of z is also analytic, right? So I'm saying z is analytic. So z square, z to the n, these are all analytic functions, right? Now sums of analytic function is also analytic function. So any polynomial a n z to the n equal to 0 to capital N. So this is nth degree polynomial, some polynomial. I call it P capital N Z, right? This is also analytic. And also you can, this series could also be infinite. I mean, this n could also go to infinity. Of course, then it may not be, it may not converge. So you have to have convergence conditions and so on. So infinite series, a power series, this by the way called power series, n going from 0 to infinity, okay? If it is convergent, right, then it will define some function, say call it P of z, if it is convergent. So I'm assuming this convergent. So assume it is convergent in some region. It is convergent in some region. Then in that region, again, this will be analytic for the same reason, because anyway, all these polynomials are, right? So this also. So an example of this, which is a very useful example, is exponential of z, e to the power of z. I mean, you all know exponential of a real number, right? It's simply given by this series, 1 over factorial n z to the n going from 0 to infinity. Right? I mean, you have seen it for the real x, right? But you use the same definition, right? So this is by definition that. Okay? This is, let's say, a symbol for that. let me see this. It's a symbol, but it's a bit more than that, more than a symbol. You see, I mean, when you write something like this, it's not just a symbol, I should say. Okay. When you say even e to the x equal to that, 1 over factorial n x to the n, for x real. I mean, this you have seen, right? N equal to 0 to infinity. Now, if you take e to the power of x times e to the y, when you write something like this with exponent up, you would imagine that it should add up, right? So this should add up to e to the x plus y. So this is something you have to check. I mean, it's not at all, I mean, from the definition that we have given here, so you use that, put this infinite series here, put the infinite series in y here, and the product should be again in infinite series in x plus y. It's not obvious. You have to work it out. So that's why in the beginning I said this is just a definition, but it is not. It's more than a definition, because when you're writing like this, you are assuming this product rule. No? So this product rule you have to check it. I mean, this you have done it, right? I mean, you are familiar with this. That if you define this guy e to the x like that, then it satisfies this equation. It's again the same rearrangement trick of the double sum into, it's again the same, actually the same thing what we did for the Taylor expansion. If you take the, okay, let me just remind you what happened. So if I take this guy, so this this e to the x times e to the y is clearly, so x to the n factorial n, say y to the m factorial m, right? N going from 0 to infinity times this, so this times that, right? M going from 0 to infinity, which is the same as n m going from 0 to infinity, 1 over factorial n, 1 over factorial m, x to the n, y to the m. Now again do the same trick that we did before. We sum it in a different way. We keep n plus m fixed first, and then distribute in different ways the powers of k, x and y. So this I can write it as sum k going from 0 to infinity and L going from 0 to k, okay? And then you have 1 over factorial L, 1 over factorial k minus L, x to the power of L, y to the power of k minus L, right? The same trick that we did before. And now you can do the thing, you can, let's first sum L equal to, first let's do the summation over L, but this is exactly the binomial. I mean, if you multiply and divide by factorial k, this is just the combinatoric factor kcl, and you have x to the L, y to the k minus L, but that is the same as x plus y to the power of k. So this is x plus y to the k over factorial k, and then k, and then you have to sum over k equal to 0 to infinity, but that by definition is exponential of x plus y, right? So it's the same, that same trick you use to, the rearranging the sum, you use to prove this. Okay. Now, so this is a power series. Actually, this has this is convergent. This is convergent, and the radius of convergence is infinite. This is convergent in the entire complex plane. Okay. I mean, this follows just from the. I mean, if you know this result for the real part, it follows for the complex case, because if you just take the modulus, if you take the modulus of this object, modulus of 1 over factorial n z to the n, sum n equal to 0 to infinity. Well, again, using a triangular inequality, this is a sum less than or equal to n equal to 0 to infinity, 1 over factorial n, modulus of z to the n. But modulus of z is a real number, so if you know that this is convergent, then this is finite, right? This is some finite expression. So the modulus of this object is finite, so therefore this object itself is finite, right? This complex number itself is finite, so that's the way to prove. So it's bounded. I mean, this doesn't blow up anywhere. This infinite series can be summed and gives you finite answer for any value of z, for any finite value of z. So it's infinite. So it's in the entire complex plane. One interesting thing is this. Okay, this is now for arbitrary complex number. What if that complex number happened to be pure imaginary? So z is x plus iy, right? So put x equal to 0. So suppose I'm looking at, in that case, you have e to the power of I, say y. Well, that has expansion. You just substitute this here. You get 1 over factorial. So yeah, it will be like, let me write explicitly, 1 minus 1 plus iy minus y square by 2, minus because I square is minus, plus minus I y cube over factorial 3 plus y to the 4 over factorial 4, etc. So you can see immediately, if you separate out the real imaginary part, this is 1 minus y square by 2 plus y to the 4 by factorial 4 minus y to the 6 over factorial 6 and so on, plus I times y minus y cube over factorial 3 plus y to the 5 over factorial 5 and so on. Do you recognize these things? It's cosine, right? This is the Taylor expansion for the cosine of y. This is the Taylor expansion for the sine of y. So therefore, we are saying that this object is cosine of y plus I sine of y. Okay. This means also you can use this to write a convenient expression. So given a complex number, some complex number, this will have some, this will be some x plus I, x and y coordinates, right? So z is x plus iy. So let's look at e to the power, so let me write it like this. I can write it like this. Go to the polar coordinate. So this is r, say this is the length r, the polar coordinate, and let's say this angle is theta. Then x, this is x is r cosine theta, and y is r sine theta, right? So this is the same as r comes out as a common factor, and you get cosine theta plus I sine theta, right? Because x is r cosine theta, and this is the y, that is r sine theta, right? So I just use that. And now use the fact that cosine theta plus I sine theta is e to the I theta. So therefore, you can, in the polar coordinate, this z is nothing else but r times e to the I theta. E to the I theta, yeah. In fact, you can see also what is e to the I theta. E to the I theta is a modulus 1. Because if you take the modulus of e to the I theta, that by definition is a square root of e to the I theta times its complex conjugate. When you take the complex conjugate, it's just minus, right? So e to the minus I theta, and use the fact that the product of two exponentials, you just add the exponents. So this becomes square root of e to the 0, which is 1. So it is 1. So it's a unit circle actually. If you, as you change theta, what you're going, from theta equal to 0 to 2 pi, you're just taking a unit circle. This e to the I theta. E to the I theta is just going in a unit circle. And r is just the length. So this will give you a circle of radius r as you change theta. So this is a convenient way of writing. In many applications, we'll when we have some integral, sometimes it's convenient to change the variable to theta or r. No? We will see that, but using this relation, we will change the variable integrations. So what other example? Okay, let me just give you some definitions now. Give some definitions of, is there anything else I have to say? Some definitions. But I have already said it, but I just to say it again. So you say a function is analytic. Function is analytic at some point, say z naught, at some point z, at some z naught, say, if it is differentiable at Z0 as well as at Z0 and all the points in some neighborhood. In some neighborhood. NHBD will stand for neighborhood. It's just picture is like, I mean, if this is the point Z0, then there is some neighborhood, could be very, very small, doesn't matter, but some open set which contains that point. So what we are saying is that you say function is analytic here if it is differentiable everywhere inside this. Right? So there's some small neighborhood. Okay, so then that's one thing. And then there is if a function is given, if an analytic function is given, then the entire region where this function is analytic, the region where it is analytic is called the domain of analyticity, is called the domain. Okay, it's not very, I'm just saying some definitions. Domain of analyticity. Okay. So in all the, okay, as I said, this analytic of course means some neighborhood, right? But it could be that it's analytic even in bigger region, no? So whatever that region where it is analytic, that is called the domain of analyticity, right? Now, if a function is analytic, if a function is analytic in the entire complex plane, if a function is analytic in the entire complex plane, in the whole of complex plane, then it is called an entire function. Then it is called an entire function. For example, all the polynomials in Z, they're entire functions, or the exponential of Z, that's an entire function, right? So these are all examples of entire functions. But I mean, an example where something is not an entire function is take 1 over Z. So 1 over Z is perfectly okay if you're not near the origin, right? If you just look at some point here which is not the origin, this will be analytic here. Okay. You can explicitly check that it satisfies the Cauchy-Riemann condition. Anywhere except the origin, it will satisfy the Cauchy-Riemann condition. I mean, actually, you can please try to do that. Check it if it's analytic or not. If it satisfies, just split the, I mean, take the real and imaginary part and show that it satisfies the Cauchy-Riemann condition. So, except at origin, right? So this is analytic except at origin. Okay. So, I mean, such a function, I mean, so you say that this function has a singularity at origin because it becomes singular, it becomes blows up, right? So you say this function becomes singular at the origin, but it is perfectly fine everywhere else. Huh? So this you say that this is singular. So this function, it has a singularity. Okay. But it's an isolated singularity, you see, because it's just at origin, right? Or more generally, you could take a function which is say 1 over Z minus Z1. Z1 is some number, some complex number. 1 over Z minus Z2, etc. Right? So it could be Z1 is here, Z2 is there, etc. Right? But if the Z1, Z2, etc. are isolated points, I mean are separated points, then you say that this function has a singularity of the isolated type, the isolated singularities. Okay? But if there is some situation where there is an accumulation of singularities, okay, that will be example of not isolated singularities. I mean, what does it mean isolated? It means, so there is a singularity here, but there is a neighborhood around it where this is the only singularity, right? That's what we mean by isolated, right? Because the another point Z2 here is, I mean, I can always choose some neighborhood which is which does not include Z2, right? So it's isolated in the usual sense. It's isolated, no, in the usual sense. But there could be examples where it's not. I mean, you know, you might have situations where, for example, let me try to see some example. Say 1 over sine pi over z. Let's see. I mean, this, you know, sine of any integer times pi is 0, right? So this will become 0 whenever z is 1 over some integer n, right? Because if z is 1 over n, this becomes sine of n pi, and sine of n pi is 0, and this is the denominator, so it blows up, right? So whenever z is equal to 1 over n, this blows up. There's a singularity. But now you see this is not isolated because this, I mean, for every n, right? So I mean, 0 is not an isolated point. I mean, n going to infinity limit, you get 0, right? And that 0 is not isolated. You cannot find any neighborhood where there is no other singularity, right? This is this sequence. If you look at the sequence of 1 over n, sequence of 1 over n, as n goes from 1, 2, all the way up to infinity, this converges. It converges to 0. In the n going to infinity limit, you go to 0. So what it means that for any epsilon, you can always find a point in an element here which is inside the distance epsilon from 0, right? So therefore 0 is not an isolated point. So I'm saying that this is a counter example. I mean, this is not an isolated singularity. In this chapter, we'll be actually only discussing isolated singularities. We will not be discussing these complicated issues. We'll be only working with isolated singularities. And even isolated singularities of a particular type, but that I'll come to later. I mean, that further classification of different types of isolated singularities. Of course, it's not just 1 over z. You can have 1 over z to any power, k. K is positive. K is some positive integer, let's say. This will all be singular at only origin. Everywhere else it will be fine. It will be analytic, right? But there are also other types of situations where you can have, which is, for example, let's suppose I take square root of z. This is a problem with the following, that remember z in the polar coordinate. In the polar coordinates, you have theta, r. The z was nothing else but r e to the I theta, right? So square root of z is square root of r. Okay, r is a positive number, so that's pi. That square root is perfectly makes sense. But this becomes e to the I theta by 2, right? Now remember, when theta goes from 0 to 2 pi, you come back to original value of z, original point. But you see, the square root of z, when you take theta going from 0 to 2 pi, it comes back with the e to the I pi, because 2 cancels with this 2. And e to the I pi is not 1, it is minus 1. Because remember, this is cosine of theta by 2 plus I sine theta by 2. This exponential is that, right? So if you take theta equal to 2 pi, this is cosine pi is minus 1. Okay, this is 0, but it's minus 1. So you don't come back to original value. So this function, you say this function is multi-valued. It is not single-valued. So at this point, if you take this point to be theta equal to 0, you get one value. But you can also equivalently this point, you can take it to have theta equal to 2 pi. But when you take it as 2 pi, it's a different answer. It's a multi-valued function. This is an example of multi-valued function. More generally, if you take z to the power of any 1 over n, let's say, where n is some positive integer, n is any integer, positive or negative, doesn't matter, then this is the same as r to the 1 over n, e to the I theta over n, right? So in this case, as you take theta from 0 to 2 pi, you pick up a phase e to the 2 pi I over n, right? You don't come back to original value. In fact, you have to go n times around to come back to its original value. Right? You have to go, if you take theta going to theta plus 2 pi n, what does it mean? You're going around n times. Then you come back to original value because you shift theta to theta plus 2 pi n, nothing happens because e to the 2 pi I is 1. Right? But if you do only once, you come back after one rotation, you don't come back to original. 2 rotations, you don't come back to original. You have to make n rotations to come back to original value. Right? So this is an example of these are all examples of multi-valued functions. So these are also singular, but of a different type. Here the singularity is not that it's multi-valued. You see 1 over z to the k, where k is an integer, is not multi-valued. I mean, you go around, you will come back to original value. Right? Only thing is that it blows up at origin. So this is a different type of singularity, that's a different type of singularity. This is to do with the multi-valuedness. The function itself is not defined. We will actually discuss both of these things, both of these such types of singularities as well as this multi-valued, and we'll show what the aim of this thing is to first of all prove some theorems which are like Cauchy theorems and so on, and using those theorems you can evaluate lots of definite integrals, okay, using for both this case as well as that case. Quite non-trivial integrals which will be very difficult to do it without using these techniques. Okay. So we will see the usefulness of that. Now I don't know, I think there's no point in, the next step was to actually prove the Cauchy theorem, which is, maybe I do it next time, because that is, I think that you need to really understand, because that is the essential part. Yeah.
Would you mind repeating this part again?
This part?
Yeah.
So what I'm saying that this is all this. Let's take square root of z. Square root of z is the same as that, right? Now, take so this is that cosine theta by 2. So this is the same as square root of r times that. Now, take the you start. Suppose you start from here, and you go around along a circle. Okay. So when you're going around along a circle, r is not changing. R is the same, but theta is changing. Theta goes from 0 all the way up to 2 pi. Right. Now, if the function was single valued, right, as you go from 0 to 2 pi, it should come back to its original value. Right. Suppose the function had some value here. Now you keep changing, keep moving, and keep finding what is the value of the function here, 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 here. Finally, come back, and if it is single valued, it should come back to its original value. Right. But here, what we are seeing at theta equal to 0. Okay, this is not there, and this is cosine of 0, which is 1, right? But when you bring it to theta equal to 2 pi, this becomes minus 1. That is still 0, but this is minus 1. So you see, you're not coming back to its original value. So at this point, you cannot say really what is the value of this function, whether it is simply r or minus r. You don't know, right? This is always the ambiguity. When you take a square root, there's always a plus minus ambiguity, right? That's what it is actually, plus minus ambiguity. But the point is that, okay, you can choose something. Suppose I say it's plus, fine, here. But then it has to vary continuously, right? When it varies continuously, and then you come back here, you find that you have suddenly come back with a minus sign because of this. You see, you change theta continuously. So I choose say the plus sign to begin with, right? Then I start changing continuously theta and 0 to 2 pi, and then suddenly at 2 pi I find it's minus, right? This is the problem with that. This is a problem in a complex plane, because you can find contours, you can take a path and come back, right? For the real case, square root has, okay, plus or minus ambiguity, but it doesn't concern you so much. No? You choose some root and that's it. You choose, you don't. But in the two-dimensional space, you can come back in different paths, no? And then you find that you're not coming back to its original value. Such things are called branch cuts. There's a branch cut. What you do in such cases, you start from, everything is happening here, you see. For example, if you take a point here and go around and come back, okay, and change this theta continuously, you come back, you will come back to its original value, right? Because, okay, if you look at the theta is going up to some maximum value and coming back again to its original value, right? So this function will be the same. So if you choose a path like that, you will come back to its original value, right? Problem is only if the path encircles, it goes around the origin. That is where the problem is. So what you do in such cases, you choose a cut. You cut this plane into, you sort of take a scissors and cut it. No? Just imagine to cut it like that. So you cut it, and then you say that when you go around and come back, you don't come back to the original point. You come back to a second sheet. You imagine that you put another sheet also, right? And sort of glue the lower part of the first sheet to the upper part of the second sheet. Okay, and then now that's impossible to imagine, but the lower part of the second sheet you glue to the upper part of the first sheet. That is impossible to imagine, but I mean mathematically you can still discuss that. So you say you go around, come back here, then you don't go to the first sheet, you go to the second sheet, then you go back and come here, then you go to the first sheet, right? So you enlarge the space. So enlarge the space by putting several, okay, for this was for the square root. If you have 1 over n, then you will need to put n sheets, right? Always successively gluing the lower part with the upper part of the next one, and so on. And finally, for the last one, you glue to the first one, right? And on this enlarged space, that function will be single valued. You see. So this is a technique, I mean, of going to this. We will discuss it in much more detail later on, because I will use these techniques of putting in many sheets. This is called a branch cover. This is called a branch cut. This is called the branch point from where it starts, this cut, right? And this sheets you add, this called the branch covering. Okay? So what we will do is that we will carry out several integrals involving such fractional powers, right? Using this technology of this method of branch covering. Okay. So at that point I will discuss in more detail.